everybody, to the CURE panel from the Center for Teaching and Learning. I'm Sadie, Otte. I'm one of the CTL faculty co-directors and also organic chemistry lab coordinator at the Keck Science Department. So before the panelists introduce themselves, I wanted to get a quick poll from the audience and see kind of where you're all at when it comes to cures. So how many of you feel like you have a good understanding of what a cure is? So most of you, okay, that's great. And how many of you have done a cure before or something like it? Good. That is really helpful. Yeah. Thank you. So I wanted to go over like the definition a little bit first because I think it's still evolving and not necessarily something that everyone has the same understanding of, but it is different from inquiry-based or even project-based learning in a few ways. So for one thing that people generally agree on is that there's a discovery aspect to a cure where the outcome is unknown. In addition, there are scientific practices, so students think about hypotheses, they think about the literature, like what's been done, what is the current state of the field, and what can they do to kind of push that boundary. The work is in some way broadly relevant or important, so it's authentic, it's actually being used in some sort of wider study, not simply just done for its own sake. And ownership, that students feel ownership over the project and responsible or accountable for the things that they're producing in some way. So again, not everyone may agree on all of those things, but that's just kind of an idea of kind of where most people are landing with cures. So now, I'd love it if each panelist could introduce themselves in 5 minutes or less, and then we'll open it up for questions. If you want to just start handing it down, that'd be great.
So my name is Leconte. I'm in Keck Science in chemistry. I'm a biological chemist, so most of the things I've worked on have been sort of at that interface between biology and chemistry. I'll try to keep this short because I'd rather have lots of time for questions. So I'll just say my experiences with cures when I was reflecting on this were really varied. So when I was an undergraduate, I had a class that was an advanced chemistry lab class that was a cure. So I took it as a student, and then I TA'd it, which was actually maybe one of the most useful experiences I had as an undergraduate. And then when I came here, and those were like 3 of the 4 criteria. So I was listening to the criteria. I was like, was it a cure? 3 out of 4 things were checked off. And then when I came here, I've taught in our interdisciplinary biology and chemistry class. And so I created an interdisciplinary cure for first-year students. And in that, we were basically just doing some simple enzymology, where students would pick an amino acid, they change to alanine, and make some measurements on how that changed the function of the enzyme. And then I've started a class more recently that's a sort of bigger project-focused class where we're trying to use sort of direct evolution methods and identify novel proteins with new function. And that's an upper-level biochemistry majors class.
I'm Sara Olson. I'm in the Pomona biology department. And I didn't have any cures when I was an undergrad. I'm jealous that you got that chance. But when I was transitioning from my postdoc to my faculty position, I recognized the importance of keeping the research program going during the academic year. And also, of course, the main objective, right, keeping students engaged. And so I just started integrating from my first year here. I've been here 11 years now. But just put my research project into my advanced cell biology class. So I've been doing it 11 years. I've never taught the same lab twice. Every year it's been different, and it depends on the trajectory of where the research project is going in my research lab. So it's an advanced cell biology course for 24 students. So I have them split into 2 lab days. So 12 and 12. We run about 8 different projects through the semester. And the thing that stays the same, right? I don't want it to make it sound like we have to reinvent the wheel every year. It's not quite like that, right? We keep the same foundational experimental techniques every year. So they learn how to do microscopy, fluorescence microscopy, and co-immunoprecipitation, and Western blotting, and gene inhibitions, and things like that. So they learn the same techniques, but the focus, the research idea changes every year, depending on what the lab is doing. And so even when we're learning common techniques, the students, each group will have a different protein that they're studying. So some years, like I introduced the proteins that we discovered the year prior, right? And we want to learn more about them. Some years, the students will hunt through the literature, right, and hunt through the databases and try to decide what protein they want to study. And so it, kind of just varies year to year depending on where I kind of want to take the project. So I provide the big picture overview, and then the students are the ones that are designing what the individual projects will go. But I love the creativity that goes into it. I love the independence and the feeling ownership over the project that they have. More recently, we put CRISPR into the lab, so it's been kind of fun. We get to teach CRISPR, and everybody gets to choose their own edit and how to do things. But I guess I'll leave it for there now. Yeah, make time for questions. It's a lot of fun.
My name is Sheung. I am a physicist at Keck Science. I would say that definitely I did not take a CURE as an undergrad. I tried multiple times to incorporate different aspects of the definition that Sadie was talking about into different classes. So my first attempt was when I was a lecturer at the University of Illinois after my PhD. I took over a module in the advanced biophysics lab and had 4 students try to build on top of a teaching journal article. So there's a discovery aspect, but also some scaffolding up to that point. And then later on here, the stable class I'm teaching, I would say it's not quite a CURE, more like a very project-heavy class, is the electronics lab, where they definitely have a sense of ownership of a project that has like a month of in-class time for them to come up with their own idea of what they want to build using the knowledge in the field of different electronic circuits and different devices that we will redesign, but apply it to their day-to-day life. And so there's some discovery aspect to that, but I would say it's not scientific. And then another thing I've recently done is I kind of collaborating with a collaborator who's also an RUI, and we were trying to do something where we introduced like current research into their advanced physics lab, where I was the person supplying data, in my case microscopy videos. We were doing some tracking of DNA to look at how they are transported through an intracellular environment. And so that was where I would say in order to do it in physics, we have to either choose for them to do analysis only or do the taking data only. It's pretty hard to do both together, so I'm still thinking about that problem. And I'm generally just thinking about a way to make it a stable component of a class I'm about to launch, which is the Advanced Physics Lab here at Keck. Yeah, so I'm happy to discuss and hear ideas.
Yeah, I'm Dave Vosburg. I'm an organic chemist at Harvey. Been there since 2005. And I guess I did, in retrospect, do something kind of CURE-like as an undergrad in advanced organic lab. I did have one where it was a kind of coherent project that we all had different aspects to it. It was making new molecules that no one had made before. So I did that, I guess. Well, that's probably more modest than what I'm doing now. So when I came to in our second semester organic chemistry lab, which is essentially now it is a sophomore spring course, the second half of the course is students can make kind of whatever. And when I came, that was the case, but it was just like, go find a paper, go make a thing, as long as it's not illegal or too expensive or super dangerous, like go for it. But then it's like, then you have product and then you just throw it away at the end. It's like, this is perhaps not the best. And so after maybe 2 years or so, I started to say, well, actually, here's a molecule I want. And so how about somebody tries to make that? Here's the molecule that she wants. How about we try to make that or whatever? And sometimes like, this is a project that might work and it might not. Like, if this works, for a student for 5 weeks, then maybe I would actually commit a regular research student to it. But it's a low commitment of 1 out of, say, 5 to 12 students in a section of lab to just try it out for a while. So they kind of get to do that. It is very chaotic because they're all doing different things. None of it I've ever done before, almost entirely. And again, they're all different, and they give presentations. They're totally different than each other. Multiple papers have come out, like JChemEd articles mostly. But then like 5 different thesis students, their projects came out of something that started in this kind of venue. And a couple of hope for papers soon out of that, in addition to sort of chemical education stuff. So it's super interesting and fun. You kind of try out a student that might be a researcher in your group down the road, especially with their sophomores or used to be juniors for us. It's like, oh, if they're really productive there, it's like, hey, you want to continue on either this or something like this? We have, this is where to do it. So that's been a lot of fun and exciting. And Spencer's about to jump into this too this semester because we're starting like this coming week. They proposed a project. And we have, also I will note that one thing that I did is start to specifically say, here's some recommended projects. You don't have to choose from this list, but these are projects that I care about. You can pick something else if you really want to, but these I care about, and it might, I will work a little harder to help you with these ones if you versus your own is sort of how I kind of pitch it. So But it's been a lot of fun. It's my most exciting part of the semester for sure, and their presentations at the end are super interesting. And so yeah, but you know, and they don't have to, just showing up to the lab each day those weeks, it's like, all right, what's going to happen today? I have no idea, right? Hopefully not a fire, but you know, that's kind of how it goes.
Thank you.
Yeah.
Hi, everybody. My name is Jason Torr. I've been here for about a year and a half in Keck Science. I'm the Integrated Sciences Lab Director. And prior to that, I was at Hampshire College in Amherst, Massachusetts for 19 years, something like that. I started teaching in 2002, pretty much fresh out of graduate school at Hampshire College. And in those days, we didn't call them cures. I don't know who the lucky person was who coined the sort of acronym and that publication, but that's just how we taught. That was basically, a cure is basically the pedagogy of Hampshire College. All the science courses were taught that way. And so I didn't know another way. I just stepped in, they said, this is what we do, and that's what I did. It turns out that it's a great way to teach. It's a great way to teach science. And so I've kind of been doing it all along. I've been doing it for first year students. I've done it for more advanced students, small classes, large classes. Courses that have been more field-based. So I'm a microbiologist, environmental microbiologist by training. Some courses have been more field-based, some purely lab-based. And you know, I feel like I've met my people up here because everything everybody has said has sort of resonated, although I have not personally experienced great success at publishing in journals with cures, but the success of students has been remarkable. We have done poster presentations at conferences, things like that. But in particular, I find them to be excellent places for students to find a place in science, discover that, oh, I can do science, and there's a place for me here. And to go on, so it's a great hook, and they go on, and they'll be great thesis students in many cases. And I've had students who have come to college, and I have to take a science course, but I'm an art major, and then discover, no, I love science. And it's really a result of, I think, the nature of the cure, where they get to dig in and actually, it's not science the way they did science in high school. It's science the way we do science, right? It's the way it's actually done. And so I think it has these tremendous strengths. So I'm continuing to try and do that here. I'm teaching the lab sections, or coordinate the lab sections of IBC. And one other aspect of, I'm not sure if it came up or not, if anybody else has mentioned it, but it's always been a priority for me working with students is that we take on projects that have a broader context, that are important in the world, that maybe an environmental problem, a problem that people care about and that affects people. So right now, we're doing a project, and I'm working with Katie. We're kind of collaborating across Advanced Chem Lab and IBC to look at problems in water, in drinking water, particularly in underserved communities, and so the students are working on that problem in the context of both biology and chemistry, but it's very much a cure. It's a little bit more mentored at the introductory level than it would be at the advanced level, but it's still a cure. So I can say more, but I'm sure there are questions.
Yeah, thank you so much. I really appreciated getting that little bit of introduction to what each of you do. And I would really like to make this conversational, so if anyone has questions, feel free to jump in. Maybe I'll take the first question, but really, anytime that you want to participate as the audience, or if panelists want to respond to each other, I'm totally open to that as well. So I guess for a little bit more, going deeper into what some of you have already touched on, which would be some of the benefits of doing a cure. If each of you could talk a little bit more about how you decided to do a cure, how you got interested in it, and how your learning outcomes change when you do a cure, and if you had to make trade-offs and why you felt that was worth it, or if you feel it's worth it, and why. And maybe we can start with Sara this time, so we mix it up.
In terms of changing learning outcomes, I didn't have to change anything because I've only done it this way. So it's not like I went from a traditional lab to a cure lab. But when I'm seeing the difference in learning outcomes between maybe the introductory class, which I teach, right, but the lab for that, which is more kind of structured and guided versus this one, which is more CURE-like, or which is a CURE. The learning goals and outcomes are roughly the same, right? It's like to explore the literature, to be able to mine the literature, to identify an unknown question, to develop a hypothesis, to design your experiments, and to test them, and to analyze the data. Like, those learning outcomes don't change. The idea of presentation of that data, right? The oral presentations we have, the poster presentations, writing a research proposal, like, that's all identical actually between the two different courses. It's just the idea of excitement, and I'm actually doing research that nobody knows the answer to, right? There's a lot more engagement from the students when they know that I don't know the answer, and that they know that they're the first person that's ever going to discover this. There's just a lot more investment that way rather than, okay, I'm just going through the motions and checking off the box. So that would be my opinion, is that, like, I don't really change the learning outcomes. That would, what else was there? I think that was the main thing.
That was the main thing.
Great.
Yeah, thank you.
Yeah, so I guess I definitely, in physics, the typical way advanced lab is taught is it's little modules where students are shown or are asked to reproduce seminal experiments. For example, melting overdraft, or like the speed of light, or things like that. And so for me, being trained to teach in that way, I really did have to think a lot about how to change that grading rubric, and is it worth the time and effort? So I can say that for me, and I'm very much come up the side of, I definitely want to teach a CURE when I'm controlling the lab. And it's because within physics, I don't know how many of you are familiar with like the material we cover in physics, but basically there's like the cosmic mechanics, which is like apples falling and planets going, and then electricity, magnetism. And then there is statistical mechanics, which is like the gases and the fluids. And then there's like, quantum mechanics, which is the tiny stuff, right? And when an undergraduate student goes through a physics program, they will often, until like the first 3 years, they will maybe have spent maybe 2 weeks of the first 3 years on anything that enters the 20th century, right? Because they learn about Newton, they learn about like Lagrange, Laplace, whatever, and by the time they get to Einstein, that's 1905, right? And that's the stuff people think is mind-blowingly complicated. And so the fundamental, I guess, gap I wanted to address with the CURE is students I talk to, like majors that already have a physics degree or about to get a physics degree, they feel like the physics they learned come out of a book and it's dead. And they don't question the equation they read in the book, right? It's not a concept that it might be wrong. And the only way I've come up with that I can address this is to introduce like current research somehow. And in physics, the laboratory environment is the best way to do it, And so, and then just to briefly go over the rubric, I personally feel very strongly that it's unfair to grade students on anything that has a chance of luck involved. And so when it's something that even I don't know what the outcome will be, right? Obviously, I can't grade them on the outcome. Whereas it's very easy to lean back on that on a lab that, was done 200 years ago and was like a Nobel Prize or whatever. That oh yeah, you should have gotten the charged electron is, this, right? But when it's a CURE-like project or like a really very free-form project, like I'm teaching electronics lab, I've had to carefully look at my rubric and ask myself, how much am I weighting this towards foundational skills that they were taught? Like, you knew how to build this kind of circuit because you were taught to. You knew that you encountered this problem in your project and it was a way to solve it is to use this circuit. But I don't grade them on whether the project worked. So yeah, and I'm still revising the rubric, but that's a lot of thought went into it.
Yeah, great. For me, I said already, not having waste stuff that is dumped or whatever, but having value beyond the student and their experience themselves. So it's more exciting to me if something new, like if I don't know what's happening, it's like, oh great, cool, let's see what happens. I don't know, and so it's troubleshooting the whole way. So it's like super exciting and fun, and like I'm never bored during that at all. There is extra prep work at the beginning potentially, particularly if I'm seeing like, hey, there's 12 different options, like thinking of things. But as I'm perusing the literature just generally, I'm like, oh. Or I go to a conference, like, oh, that might. In fact, one project was one I went to a conference. I saw a talk. It was like an award-winning talk. It was like best paper of the year in this journal. And I talked to the speaker afterwards. Said, oh, that's like super cool chemistry. I bet we could do that in undergrad lab. So, oh, let's do this. So like, boom, collaboration. And so we published a JKM article on that after a couple of students tried that in a kind of CURE setting. And actually, those are only two. It was only those two students really? And then like, boom, next semester, let's do it in the lab. We actually did it online during COVID too, and published kind of both, how it worked virtually and how, obviously they didn't make chemicals in that case virtually, but they were able to analyze things and go deep on the green chemistry and the mechanism kind of stuff, which worked really well. So like that's been a reason for me, and it's super fun to see how they grow during it too, because the rate of growth, even if it's only like 5-6 weeks in the lab of doing that versus the rest of the semester, it's a really big change. It's a lot of fun.
Well, I think I mentioned in terms of why I started teaching at CURE, because that's how it's done here at Vosburg College at Hampshire. I think I continued to do it because I loved it and I could see the benefits to the students. Initially, I think fresh out of graduate school, I looked at students like they're, my little minions there to help me with my research that I'm trying to get published, or maybe making little mini-me's, but it didn't take too long before, I really started to recognize the uniqueness, the individuality that students can bring to CURE projects, that they can bring their own personal experiences and backgrounds, wherever they come from, whatever they've done, bring, in many cases, their own creativity and their own unique types of questions that they like to ask, and their own ways of thinking about things. And that, for me, was when I think light bulbs went off for me. It's like, wow, this can be really amazing. And what actually I think probably has ended up happening over the last 20 years is I've probably learned more from them than they have from me as a result of doing this, I think. I'm not sure, but that might be the case. And it's in part because of their curiosity, their interest. I've learned, I moved into areas of research in those 20 years that had not been areas of research I've been thinking about, but that because the students, 18-year-olds, are in touch with a culture, a life that I'm not in touch with. Definitely not right now. Very, very easily anyway, right? I mean, they're thinking about things and they're aware of things in a way that I'm not, and they're my conduit to the future, so to speak, right? Because they're looking at the future and I'm trying to figure out where they're headed. And so I've learned and moved into areas of research that I had no idea were going to be big things. Like I said, I'm a microbiologist. Like we were doing projects on yogurt and probiotics long before there were any publications in the leading microbiology journals on those things. I had no idea, but they knew. They knew that that was an interesting thing because they were in their sphere. They were talking about it and thinking about it, and so. Like I said, that's why I continue to do them, because I think it keeps me, thinking like a 19-year-old a little bit. I'm trying to hang on to that a little bit. In terms of I think you also asked about learning outcomes. Yeah. I probably undervalue content knowledge a little bit. I just don't pay attention to it very much. I'm really interested in skills. Can you find literature? How do you read it? Your quantitative skills, all those critical thinking skills. I just focus on those all the time. And over time, more and more collaborative skills, right? I mean, it seemed like 20 years ago we were talking a lot about, there's a lot of sort of this individuality, individual research skills and stuff, but it's somewhere in between we started realizing that, you need more collaborative skills. Scientists work together, right? We're not all mad scientists working in the basement alone. And so I started building in a lot of collaborative activities, working in teams. How do you work as part of a team? And that's turned out, obviously we see the world we live in now, but that I think is probably one of the most important things that I've included as part of my CURE. It's not science, but it's an essential skill, right? So we have these opportunities as a result of doing CUREs to build in these other things that students need as they go out into the world, and they can build on those things.
Yeah, so the first part of the question is why do it, right? So I think, how did I get started? Yeah, so I think as an undergraduate, I liked chemistry. That's why I decided to major in it. I didn't really know what chemists do or what research was. And I think part of it just connects to sort of my own background. I didn't really have anyone in my immediate community who was a scientist. I didn't really know what scientists do. And I just by accident ended up getting a research position just because of a friend of mine helping me out the summer before my junior year. And that was my first like lab experience. And that was like a pretty mind-blowing thing. That was like the point where I started to really love chemistry, is sort of seeing it in action and getting to do it. And so kind of my motivation in coming to an environment like this is you get to be the person who does that for people. So that's why my research lab is too big. But like ultimately you can only help so many students in your research lab. And so I wanted to think about how can I continue to scale this? How can I give more and more students exposure to that kind of experience that I had more or less by accident? And it haunts me. What would have happened if my friend's dad wasn't head of R&D at a pharmaceutical company? That was the only reason I got a job. And so it's bothered me my whole life. And so my whole sort of modus operandi is like to try to solve that problem. And I think this is a really, and so that was why I was like, I want my lab classes to mirror what I think is exciting and fun about research as much as possible. And so that's why I started doing it. And I think it's like it definitely happens. Like one of the biggest problems I have is when I did it with IBC with like first year students, like it was like 50 students and I had like 15 or 20 of them want to join my lab after, and you're just like, no, I can't do that. I got to like 7 and it was too many. But like, yeah, you know, I think it gives people like that first exposure. I think if that's your motivation, it absolutely works for that. I think in terms of learning objectives and like those kinds of things, I think kind of like similar to sort of Jason in that I think like technical skills are important, but there's some sort of balance between technical skills and like softer skills, and I think I value those softer skills more. I think that one of the things that is unique about a CURE that you can sort of do, and I think is a unique sort of learning objective that comes out of these, is I build a lot of repetition and troubleshooting into these by design. So it's like, you know, if you're going to do some cloning, like, you know, create some genes, you're probably going to have to do like a few rounds of PCR. And so you're going to do the first one, it's going to fail, and say, okay, how do we figure out how to troubleshoot this? And make them read things, come back with ideas, talk about it, and try again. And I think that was really built into the one that I was an undergraduate. And it was probably the most valuable experience for me was being a TA when I did as an undergraduate, because when I was the TA, I would help everyone troubleshoot. And so it was like a master class in troubleshooting where I would just run around between groups and try to help different people troubleshoot. And I realized to me that's the most important part of CURE is like active troubleshooting and learning through iteration of like how to adjust experiments and repeat. So I think that would be the only thing. I probably have like fewer technical skills gained, but more like soft skills, troubleshooting, those kind of things gained in terms of learning objectives.
Wonderful, thank you all so much. I have so many follow-up questions for each of you, but I really want to open it up to everyone else here too and make sure that your questions get answered. So if anyone in the audience has any questions, please feel free to ask. Yeah.
I'm Katie Musicar at Pomona College, and I'm currently working on a CURE that will be a first-year chemistry experience. And so we're operating on an assumption that they have no prior experience at all. And so if I'm gathering right, I think 4 of you have upper division courses where you maybe could lean on prior prereqs. And so I'm wondering kind of how much are you able to lean on what they previously learned? And then in a first year, like how much scaffolding can I do, because the scaffolding may not be as discovery-based as I want, if I need to give them the skills to empower them to be discovery-based. So just like playing with that balance and lessons learned from that.
Here's a quick question, Katie. Is it an entire semester is all the CURE, or do you build up to the CURE with other stuff first?
We're going to do an entire year.
Okay.
And so I think I'm thinking the first semester might be more skill-based and the second semester will launch into the CURE.
Yeah, right.
And using those skills that they learned in the first part and repeating those, right? It's like we learn a set of 4 or 5 techniques in the first few weeks, and then they decide which of those techniques is the right one to address the question they want to ask. So they get that chance of repetition, they get that chance of mastering the skill. So yeah, you do have to build it still, even in upper division courses, the same as you will. But it's that reusing and figuring out how to mix and match. They have that creativity.
So I was going to say sort of like with any of these, I kind of feel like, so I think one of the things that I realized when I started thinking about doing it on my own, and I went back to the people who had taught me to do it, as, like when I was an undergraduate, was how much structure there was that I didn't see. And so I think a lot of like what makes these things work is like very invisible structure. So as a student, it seemed like we were going out in the world and it was wild. And then I realized when I go back, they're like, yeah, we cut off all these different avenues that you could have gone down that would have been a mess. And I think like when I've taught at the upper level, I think those guardrails are lighter. When I have done it with first years, and Jason has too. I think there's just more structure. Like it's just much more like limited in terms of what you ask them to do. But I think it's more doable than you think. A lot of worksheets where they like work through like answer this, now answer this, now answer this, and you help them like think through the process of experimental design. That's like very structured, but it's very doable. And how do you like share worksheets and stuff? Yeah.
Yeah, I think I use that guardrail analogy as well. The interesting thing about the guardrails is they don't always know they're there. I do. I know, I'm kind of keeping them. I'm kind of moving them in this direction. They can't see them. They don't necessarily have that knowledge yet. And so it's nice for them. They can kind of move in a space. A research space, play with these new tools, these new toys. It's all very exciting being in the lab. But I know where the barriers are, I know where the edges are, I know where the problems are likely to go wrong, but for them it's still discovery, which is the nice thing. With first year students, yes, a lot more scaffolding. There's a lot more we do this technique, or I teach them a technique, and then they need to think about new ways of applying it, or a new situation in which I might have 4 or 5 ideas in mind about what they can do, but they may come up with some new ones, and that's really exciting, and we can do them. And if they don't, that's okay. I still have a couple of ideas that I can kind of plug them into. The originality of the research questions, first year students often are just not that sophisticated yet. Sometimes they are, and that's really great. So that scaffolding kind of needs to be there. As they get a little bit older, I tend to open it up. I've done cures where, it's research methods in microbiology is the class. I have no syllabus. I go in, and what are we going to do this semester is my first question, and they have to, basically tell me. But that doesn't work as well with first year students. I have ideas about ways I can do it with first year students, but it would be a mess. So that scaffolding, those guardrails, I think are important for you at least to keep in mind. They may not see them. They may not know they're there. It's still an active discovery.
Well, I just jump in and say that for me, I think about it as more of the guardrails I said, and yeah, I also think that way. For me, it's a balancing between how much class time I'm devoting to allow them to be free, and that has to match how wide the area is that they're allowed to roam. And so when they are younger, it's a tighter area, and by that I mean I teach them one technique maybe, and teach them technique so that they know if they did it right. So it's really important in terms of troubleshooting, right? Like, really their mastery is in them not only being able to apply technique, but them having the ability to sanity check themselves, right? And then as I do upper division classes, I might have them know several techniques, kind of like what Sara was saying, that they kind of have a toolkit now, and then the roaming area is these techniques added together.
Great question, Katie. Thank you. Are there other questions that you all have?
Yeah, I'll ask a question about evaluation, because with students doing all sorts of different independent things, I'm curious how assuming they need a grade at the end of the semester, how do you evaluate them all equitably? Because sometimes a research project, in spite of the students' great effort, maybe it doesn't pan out. And so just how do you do equitable evaluation in your CURE settings?
Well, okay, I guess I thought about this quite recently, actually. So this is in the context of my electronics lab, which is, again, it's more of a project thing. But I've had students continue their projects into a senior thesis, so it's very open-ended. What I try to do is I make sure that I'm evaluating the learning that was actually covered in the class in the scaffolding phase. So when I go around and I help them troubleshoot, which happens every class period during the month they're doing a project, I'm evaluating them on when they grab me over and say, can you help me with this? I'm evaluating the level of their problem-solving ability, what level of problem-solving was already done by the time they pull me over, right? And I'm also evaluating them based on they had to pitch their project. That's where I evaluate how much they were able to research the literature, have a good, deep enough understanding to plan a reasonable timeline. And I also evaluate, so for me, the softer skills I'm teaching is just time management. It's an individual project, but I also ask them to help their classmates, so there's some teamwork aspect to it as well. And that's mostly at grade, like a final presentation. So whether their project actually worked is not a part of the grade, but everything leading up to it is a part of the grade.
Yeah, for the diversity projects that I've supervised in this context, I would say about half of them work on average, like overall, it was a successful experiment. But it doesn't really matter. And I tell them that up front that, it's not unusual for it to not work. It's okay. But it's how they respond and what they do. Oh, why didn't it work? Let's think about it. What are some proposals? It might not have worked because of this or whatever. And how do you know it didn't work, right? So what did happen, right? So they can get as much out of that as they can from something that actually worked. Now, it doesn't necessarily lead to a thesis project in that case. It might be all right, let's not try that sort of thing again. And that's fine. That's useful to know. And we can move on and prioritize other things. So I think you can totally do it, in a presentation, in a report, in whatever. But to not emphasize your yield or whatever the product is of it, that isn't the measure of your quality as a chemist or scientist or whatever. That's not that, right?
Yeah, I don't focus on the outcome of the experiment. It is what it is. That's not, to me, what it's really about. It's the process. And so one of the things I really like to do that I think works really well at the beginning of the semester, I talk a lot about goals, and I have students write their goals for this semester. What do they want to get out of this experience? Out of the class. Okay, what do they want to do? I at that point have talked about my learning goals for the class, right? The instructor imposed goals, but I want them to set goals. I want them to have things in which they're thinking about and working towards that are not necessarily directly related to the goals I've set for the class. In some cases, an example could be make a friend, and that's fine with me. This is a shared experience, and building community, I think, is one of the best things cures do.
Make friends by cloning, is that
create a friend. Nowadays with AI, it's getting really interesting. But, so I ask students to write their goals, and then at the end of the semester, I have them write a self-reflection, we call it self-evaluation, where they think back about their goals, they think about their learning for that semester, what did they do, what did they work on, what were they challenged by. I provide, I ask these questions, there's sort of a menu of things that they can reflect on. So I ask them to reflect on their learning. What was challenging and hard? How did you meet those challenges? And they usually come in at about a paragraph or something like that, and sometimes 2 pages or 5 pages. It all depends on how much that student wants to write. But I think an important thing to keep in mind about learning is that learning happens in reflection. It really happens in self-reflection. That is the key moment. When you think back, right? You can read a paragraph, but you don't really learn it until you've gone back and reflected on that paragraph. And I emphasize this with students, that they need to think about what they've done that semester, the nature of all their work, where they were at the beginning of the semester. And that self-reflection factors in a huge amount. Now, at Hampshire College, I didn't have to give letter grades. We had no letter grades. It was evaluations. I could take that and write an evaluation. Here I have to give grades, and so I just added one additional question. What grade did you earn in this class? We don't have to agree, and I tell them if we don't agree, then we'll have a conversation about it, but yeah, that, and they're usually harder on themselves than I am. So I think it's a useful question for them to ponder. That's how I look.
One additional element I built into it too that hasn't been covered yet is the kind of dedication to the project. So when we run ours, right, they're signing up for microscope times. They might do genetic crosses where they're coming in on off days. And so it's not that every person is there for all 4 hours of the lab time. And so part of it is like a lab participation grade. Like, did you put the effort in that you needed to be successful in your project? And so there might be a group that comes in and replicates their experiment. You know, they get ends of 3 or 4. And another group might say, oh, I snapped my single picture, I'm out of here, right? And so you can build elements into that for students that are putting more effort into it than others. Are you trying to do everything? You know, there's a group that tried their genetic cross and failed, but they tried again. There was another group that tried their genetic cross, they failed, and they gave up, right? And so you're going to see elements of that as well, depending on how dedicated they are to the project, but that can also factor into things if you're worried about having more tangible things to grade. But the idea of the logic and the literature analysis and the developing ideas, like that is where the core of it is, not the outcome.
I think I usually couple it with really structured writing assignments, because I think that in that element of writing, they often will sort of have to think more deeply about why they made choices and communicate that, right? Which is a big part of science writing, right? Is to do that. And I think a CURE is a really good place to do that. And so all of them are they'll run a set of experiments, and their assignment for the next time will be to write the results paragraph that describes that and create a figure, right? And so they're sort of actively doing that. It also allows you to iterate on writing results sections, which is good. And the other benefit of really tying it really closely to results sections, other things work or not, you can still write about what happened and why, and interpret it. And then the nice thing is at the end of the term, if they write some sort of paper, that can be passed on to the next class, and that can be a starting point. So that has the benefit both of giving you more accessible things to start with, which is helpful, and they feel like they're part of a scientific process, right? So they're part of a sort of chain of people doing the work that are sort of trying to push things forward. And I think they get a little bit of extra, they care a little bit more because it's not just them, it's the next person who's going to pick up the work is also, they need to do a good job for them too. And I think they motivates them a little bit more.
Thank you so much.
Yeah, Sara.
I love the idea of cures. I have just been completely stumped about how to do one with the kind of research that I do. I work with wild vertebrates, and the samples are precious. We can't just spill them or destroy them. There's one go at collecting some of these kinds of data, and I just have been really stumped on how to do it. And all of you guys have these lab-based things where you can buy reagents or make them again or put them in the freezer. And I've thought about switching to other systems I don't know, snails or plants, but then they have all this upkeep, and I won't be able to do the troubleshooting because I don't know those systems so well. So I guess I was just wondering if you had, how would you think about doing a completely different system just to be able to do a cure that you don't know the research on and you don't know how to troubleshoot? Is that going to work? Because I am very worried about it. And the research that I do, it doesn't fit. And I just love this idea, and I don't know how to do it. Or maybe just let other people do it, and not in my class. I don't know.
Yeah, you don't have to do the same thing you do in your normal research lab. You can, and that can be great because you do have the synergy if that works out. But if that's not a match, you don't have to be wed to that. You're right, there may be extra effort in figuring out what am I going to do then. But I've often had parallel streams of research where I have my kind of regular make some molecules that are drug molecules in my lab. And then this other stuff, it's this other random stuff students are doing in the class that's also new. It might spin into a publication maybe, but we'll see. But it's more viable or doable or less toxic or whatever. There's a reason that I'm not having them do this, I'm having them do this instead. And so it depends on the energy you have, or if you want to do solo or someone you can collaborate with. Say, hey, I want to do this, do you want to, that could be a great thing too. Where then you do have some expertise, or you bring in some expertise, but you've got the energy and excitement and the course in which to do it, and that could be a win.
It might be a venue for team teaching.
Yeah.
Yeah, hey, possibly, Sara, I don't know all the challenges associated with your work. It's a little different than what I've done, but I would encourage you to maybe think small. Think about maybe a 3-week module within your course that might be a good place to start, maybe after they've built up some skills or some knowledge or whatever they need, something that maybe is resource light, but that you could build in this type of an experience, kind of get your feet wet with it maybe a little bit, and that you could then maybe grow out of. Because I think even just doing that, I think, is so valuable for students, even in the context of however you do your lab now. But folding that into a smaller portion could be beneficial. And the other thing is there's a lot of publications out there now on cures, and maybe you've read them, and I don't assume you haven't, but you might get ideas from people who've done little things like that.
Well, I was going to raise a resource. There's one called CureNet that's published out of Claremont College. It has lists of dozens and dozens of different cures people have put out there, just to get inspiration, right?
So I was gonna say that I think it's still pedagogically extremely valuable for students if they can't participate in the data collection phase of the research and only the analysis. So for example, if Sarah, you over the summer went with some of those students' classmates and collected some data, and you can just show some pictures or some video footage of the data being collected. And then you bring the data into the class and it hasn't been analyzed yet, right? The sense of discovery is still there, even if they didn't join you on a trip.
Yeah, I see that part, but it just didn't seem like it actually happened, because that's where we started. Like, with demo, like, oh, this is the kind of sample we analyze, and now it's analyzed in big data set, but it's not the whole experience.
Everything
That's
counts.
okay. I'm in an RCN, a research coordination network, right? And it's about bringing CRISPR into the classroom. And we've created everything from a 1 to 2 week module that's only looking at bioinformatics to a full semester long module, or like a half semester, right? Which is actually like doing the molecular biology of it. And then the full semester is putting that into an organism and seeing a phenotype. And so there's ways that these cures exist, right? That you can take bits and pieces that match with kind of the resources and availability you have in your lab. And that, yeah, like you said, that sense of discovery is still there, even if they're not involved in all of it.
So I developed a lab. So when I was a grad student, there was a lab class where there were set labs, and the last 2 months was students proposed a way to like redevelop the lab and go kind of further in it. And so I helped to develop a lab, and then 2 students went further with it, and then we wrote a JPMed article. But the peer review of that was kind of hard, and I had to redo a lot of their stuff and everything. So if you do make something publishable with the class of students, and you want to have ownership or their ownership of it, how do you submit it and then get revisions, but now they're out of your class? So how do they participate in that peer review or revision process? It's kind of holy grail question.
Yeah. I mean, you can have a whole chain of students, some of whom are gone and other ones are now involved or whatever. That can totally work. And like what role the students have in the actual writing and in like the data. I mean, like for instance, for JChemEd, it's like, oh, here's an example spectrum. It is a student spectrum, right? It's not like my spectrum. It's a student spectrum. Or this sort of things like that usually flies. I have kind of at this point, I have kind of a ritual that I do for these JChemEd things. I've done like 9 or something of this type, like that just kind of popped up almost every other year on average. And so I kind of have a rhythm, and I kind of have my head around it, and I know what is going to work. I'm happy to share what I've done. I don't know if it's helpful in your particular arena or not, but that has worked nicely. And so like getting extra data hasn't really been an issue. I mean, getting a better spectrum or whatever, like sometimes, but it's not so bad. And if it's really easy to make the thing, ultimately, if it's not like a multi-step thing, it's not super complex. Like I could, have a student remake it or whatever the next round or the next semester or whatever, or a regular research student, hey, for like a day or 2, do you want to just do this real quick? And then boom, you're on the paper too, and like help me out here. Like they're like, yeah, let's do that. So like that's just, and there's like 2 authors versus 8. Who cares, right? That's fine.
I think of the experiments that happen in class is more of like, if they work, which is a big if,
right?
Like pilot experiments, just to see like what's worth coming back to later, and then you have a summer student like actually reproduce it. Yes. Like I wouldn't trust the data that they generate as part of the class. And I always want 2 students to reproduce things anyway, so it just works out well. So I think of it as like pilot experiments, like trying things out that like you think might be interesting, and then have a summer student like follow up and do more confirmatory studies like the publishable data.
That's how we do it.
Because the students at CURE, you're not paying them to do this research. Right? They're doing research like, as part of their, I mean, they're definitely benefiting from it. But like, in a certain sense, versus a summer student, you're paying however many thousand or whatever, you're going to have a certain number that's not a large number of those probably. And so you want to kind of choose those well in their projects well. This is a way to kind of screen projects, which is a nice thing, yeah.
It's a lot of preliminary data. They generate a ton of preliminary data, and you can pick and choose what you want to follow up on in the lab with these students.
Right.
I also wanted to bring people's attention to, I don't know if it's in other disciplines as well, but in biology we have something called a micro-publication. And so this is something that's just like a single figure. It's not an entire story. And so, for ours we have like 8 different projects, right? So if we could theoretically publish 8 micro-publications every semester. I've made the choice to try to bring everything together and to get bigger papers out of it for promotional reasons and tenure promotion reasons. But if those they're starting to pop up in other disciplines now. And that's a great experience for the students too, right? Because they can generate some data. And, for me, I have 2 lab days, so I can have the Wednesday group do one replicate, and then the Thursday group do another replicate, and they have the same data, right? That's replicates. But then they can also write their own micropub, and then you can submit that, and it's a peer-reviewed paper. And it does show up on PubMed. And so I think it's starting to expand into other disciplines now, so check it out. Yeah, it's called micropublication.
Does it show up in smaller font on PubMed?
It has a little micro.
And so just related, or not quite related to the micropub thing, but a comment on the different types of teaching papers you can publish. I think there's, the holy grail is to have a normal scientific paper that was driven by your class. But I found that it's often an easier thing to reach if it's more of a, hey, I tried out this project with the students and this turns out to be a fantastic way to teach this concept, right? And so the point of the paper is more of a, this is the gap and this is now a new experiment people can do that can address the gap, and then whichever students happen to be around who took the data would then be on the paper, and other students may not want to be, still be involved, and that's their choice, because again, they're not there to do research.
Jason, I know that you experienced maybe a different kind of challenge where your data took on kind of a life of its own after the class ended. I was wondering if you could share a little bit about that with us.
Are you talking about my recent experience in the last
Bacterial samples that take over the life.
My friend bacteria?
Right.
Or maybe the data was shared in ways that you didn't have full control.
Yeah, and Katie and I are connected to this. So we started a project last spring, and we're continuing it this spring semester. We're working with a community up in the high desert, Adelanto, on their concerns amongst community members about the quality of the water. It's an underserved community, rather poor. And there's a lot of concerns about the quality of the water, whether or not it was safe or not. Some citizens were reporting very brown water. And so we got connected with this project, and both with IVC and Advanced Lab began to sort of triangulate around the problem where, largely in IVC, we were looking at some water chemistry and some water microbiology problems. Katie was working on more advanced analysis of the water chemistry. So like I said before, I like to connect with real world problems. And in this case, I would say we got connected in a way that maybe we had some political agenda, or maybe people wanted to use our results and data in order to promote a very specific position. And it wasn't really necessarily supported, it wasn't supported by really our findings. And in a certain way, it has been, so some of that information I think you have to be careful, right? I mean, we all know this as scientists, that it can be used in ways that are not intended and are not in line with what we would think and say. And so I'm trying to walk a little political line here. I know. Anyway, they misrepresented our results to some degree, or at least they wanted us to be able to say one thing right? And our results did not say that thing. Now, there's that broader context in which we are dealing with that and working within that. But then there's the conversation we have with students, right? And so this turned out to be a really great opportunity to have a conversation with students about scientific data and what we're generating, what do we think we know, okay? And how confident are we in what we're measuring, what we're observing, and what is the broader context, right? Scientific information, once we put it out there, as we all know, it can be taken by others, it can be co-opted. And so this has become part of the conversation I'm having this semester with students in thinking about our results. And so it's turned out to be a great learning experience, also frustrating. You know, when you do these sorts of community-based projects, that you are to some degree opening yourselves. I don't know how many folks do these sorts of things, but you are opening yourselves up a little bit to that. And so, yeah, it's a little challenging. I don't know if you want me to say more about that. But, yeah.
No, I just think that was not something that I would have expected. So thank you for sharing that.
Yeah, as it turned out, we didn't expect it.
Yeah.
Yeah. I think I'm probably being very cautious here, and this experience has kind of caused me to be that way a little bit more. In a way, I was very open probably a year ago, and I'm feeling a little bit more cautious at this moment. So, but it's a good learning experience. It's one that the conversations I'm having with students that I think are very beneficial.
Katie, you had a question?
Yeah, I have a question about more like prepping these kinds of experiences, because at least with Jason and I, we kind of have an idea of what we're going to see. I can order the standards ahead of time to be able to analyze these samples. But like for Dave, if you have this list of 12 experiments, but they could do anything, or Sara, you're talking about that you want to look at the protein database and pick out proteins. Like, how do you actually prep for these things, and can you get the materials the students need and time to be able to actually do them? And I'm sure, Aaron and Dan, you have issues too with yours. So.
Yeah, usually we plan far enough ahead we can. So for us, we have a C. elegans, I work in C. elegans and nematodes. So if the students are wanting to use an existing worm strain, it takes us about 2 weeks to request that strain and get it in.
Okay.
For the CRISPR experiments we do, we have to get the design done fairly early in the semester, because it's pretty quick, right? You put your thing in about your oligos in, and you order it, and it's a week later.
Okay.
So it is kind of a rush to get it ready for the next week, but we can turn it around pretty quickly. The challenge comes if we have to generate new things. So in the past, I would create new fluorescently tagged worm strains in the summer to prep for the fall, and then that's the project stuff we would be working on, right? And that became just untenable for me to try to make 4 new strains every summer. So that's right when CRISPR was discovered, right? So now I'm having the students actually. 1 year, the students will prep a new worm strain, and then we'll explore it the next semester. And so I've got this cycle kind of going now, where they feed off each other year to year. So it's not always urgent with it. So you could have multi-semester cures, like Aaron was saying, right? About seeing the trajectory of a project. But it's hard day to day. It's really hard you should see my spreadsheet trying to keep up with 8 projects, right? It's a lot to manage, and knowing which strains to have ready and which reagents each group does. It takes a lot of organization. So it's a lot in the semester, but the outcome I think is worth it for them and for me.
Yeah, I used to rely on fall break when this was a fall course, and right before that, they'd figure out what they want to do. They'd have this Google sheet or whatever, and they'd put their things, and they'd check the stockroom themselves, see if we have it already or whatever. And we'd have this kind of consolidated thing, and I'd see okay, it's not crazy expensive, this is okay or whatever. And then we order it, and it's back there in a week or longer. If it's ground ship or whatever, it takes a little longer in that case. In this case, this next week they're going to figure out their project while they're setting up. It takes half an hour to set up this other experiment that actually goes for a week. And so they're doing those together. So next week they're going to work up that other experiment. And so it's really kind of 2 weeks in advance, because we're going to start it before spring break. That's what I wanted to do. I didn't want to wait till after spring break to get going on this. And so that's what I'm doing. And so it's a week sometimes is enough. 2 weeks I feel safer in terms of knowing what they're doing. And then, or if it isn't available, okay, what do we do then? All right, we can't get that one. That's fine. That happens sometimes. All right, what's an alternative? We can figure out another thing because it's all new anyway. Let's just do something else new. That's okay. But they're each doing often very different, sometimes somewhat different experiments, individually in the course. Typically, is what I do. And then with different sections, we sometimes have a little redundancy from one section to another. But try not to overdo that. So it's not just I'm doing what somebody else is doing on Tuesday. And, they can talk, but it's nice to have their own experience and figure it out for themselves and not just rely on somebody else.
Yeah, I think like when I designed them, I don't know how you do this version. This sounds crazy. when I designed the robot very modular, like everyone is sort of doing a common set of techniques. There's a common sort of set of problems they're working on. So you have like a good sense of like what methods are going to use, so what materials you need. And I think one of the advantages, when Sara was like, I want to do a system, one of the reasons that I was like, oh, I don't think I would ever do that is because I think I have a good intrinsic sense of like how long it's going to take for things to arrive, and I can like plan and organize around that. And so I think if things are pretty modular and you know roughly what kinds of experiments they're going to do, it's doable. And it's definitely more work. It's more prep work for sure, but it's like manageable. And I think that like, I don't know what I thought, I think I just lost it. Yeah. Anyway, it's manageable. I think the hardest part is actually like when things don't work and you have to rework the schedule and keeping in mind the logistics of that. That's actually like the harder thing to like plan for, because I've never been able to like match the actual schedule. Like it's always like you're just constantly reorganizing and like, well, will I have enough time for this material to get here if I move this here and move that there? That's actually the bigger challenge. It all seems great on paper at the beginning of the term. Yeah.
Yeah, so for me, the electronics lab, I managed to get it to run pretty smoothly every year because I have a very clearly announced date. By this time, I need you to pitch your project and include it in your pitch and include your grade. It's you sourcing the items, and everyone has a budget, right? And so the people who didn't think that through carefully and have to order new other parts later, they know that their grade will suffer because they didn't think it through. And so that tended to help so that it's not like I'm continuously trying to order things, because that would have been not sustainable. The times when I've been involving students in the research, I have to say it's very loosely, or it's very controlled in that the course-based research projects follow my research lab projects. So it would be something like, I know in my research lab, this is something that's near in the paper, and there's still data that needs to be analyzed. And so in the course setting, I would scaffold it up like, here is the, kind of control that needs to be done for you to learn the technique and learn how this field works and learn how to think about the experimental system. And then here is the fresh data that you can apply your understanding to, and this is how it's new. And this actually no one knows what's going to happen, right? And so in a way, it's really tightly controlled in that they don't really get to choose the question. But I try to make sure that they get that sense of ownership and discovery.
I don't think I have anything more to add.
Yeah. Say keeping a wrangle on thing, I think it's the semester's not that long. It feels like it's huge, but really if it's 4 to 5 weeks of leading up and teaching them techniques, there's really only a short window where they're designing what they're going to do the rest of the semester, and it's really only a 1 week. I'd make them all decide, write their project proposal with a list of reagents that they need, and I only put one order in during the semester. Everything they need has to be in that proposal, and then they use that for the rest of the time. So it's not like you're constantly ordering and constantly bringing new things in. Keep it contained, keep it manageable. Yeah.
And to the extent that it's aligned with what you're already doing, you might already have a lot of stuff.
Yeah.
In some cases, you don't have to buy hardly anything.
Yeah.
But some cases, you have to buy everything, or you're like, that's too much, I'm just not going to do that. That's fine.
One point I want to add that I think helped a lot is in part of my students' project pitches, I forced them to set up internal milestones, which are kind of go, no-go points is how I think of it, right? So, students often, when you just tell them you can do anything you can imagine, right? Then some of them have a tendency to go wild, and some have a tendency to be too timid. And so a lot of my teaching is telling the timid student, okay, I think you can actually do more in this month. And then telling the student who is trying to do everything, I really don't think it's likely you can accomplish all of this, but I'm not saying you can't, feel free to try, but just my role as the instructor, making sure you have something you can wrap up in kind of a finished product, how about you tell me these milestones so that we can check in by the time we're 1 week to go or 2 weeks to go and see if you're still progressing and give ourselves some time to maybe rework a plan, right? Because I think the one reason why these experiences can end up work out really poorly for students is if they feel like they lost control of the situation, like they aim too high, and it just crashed and burned at the last week. They're in there like 10 hours a day trying to finish it. Like that's bad. So that's what I try to avoid. I think there's a lot of pedagogical value if they aimed high and then they have to go to like the half project, like a halfway point. But then it's more of the lesson learned would be project management. Oh, what I learned is that it actually takes longer. Like the first try is not gonna work, and that's okay. It just means like I need to be more realistic about what's the end point, right? So for me, a lot of the teaching this kind of course is talking to students one-on-one and meeting them where they are, and helping them define a realistic version of their own version of success.
Thank you. Other questions? So one that I had is just like how many students overall on a semester basis are involved in your CURE? And have you encountered scalability limitations? Do you have strategies for scaling up if the class gets more popular? Or do you set limits on enrollment? How do you deal with that? Or is that an issue for you?
One way you can do it is do partners or teams. Is one way. You can do that in research too. If your research group is too big, you can partner up or team up your students versus everyone has an individual thing. That is a way to go that can help just generally, I think.
I definitely prefer students work in teams, in part because collaboration, I think, has been a major emphasis, as I mentioned before. And so, plus, I find that working in teams, they can kind of pick up the slack a little bit and motivate each other. The dynamics don't always work out, but that's one way of serving more students, is definitely having team projects. It's harder with larger classes. It just is. It's once you get above. For me, once I got to like 16 students in a class, it can feel a little wild. I'm not entirely sure what's going on at every moment. So obviously, I'm sure we all love small classes, and I would definitely prefer small classes. But the bigger the class, I have found that I limit a little bit their freedom and independence to pick their own projects a little bit. Yeah, I just need to maintain a little bit more awareness about what they're doing and have a little bit more control over, again, those guardrails. You got to bring them in a little bit. Smaller classes, I'm much more willing to sort of open it up a little bit more. It can be a little bit more free form. So it depends on the size of the class. I can't help preferring small classes. I'm sure we all do. You can do so much more, but I think collaborative work is really important. It's a good skill for them to learn in the sciences, and I think it helps in this context.
Another way you can manage size is like you can have them use. I think like having like a good idea of when you want to cut them off is good. You can have them like join projects as things progress. So if they start with like 10 groups of 2 and like 3 of them, like it's just not working, and like you don't have the time and the space to start again and make it work. They can just join another group and they can write about that. That's fine. And they can sort of work together as it goes. And that's worked well for like some cloning stuff, especially where they just couldn't create their mutant. And so it's like, well, now you're going to study this other mutant, which is like pretty close. And they're still pretty excited. They still feel like it's theirs.
So like apoptosis, except apoptosis or something. Yeah. control project death or something.
Yeah. You need to have, I think Janet was saying this, I think that's like a really important point of like, you need to have a good intrinsic sense of when to stop it. And like, because I think, when I did it as an undergraduate, we had a mid-semester report where it was just like the group and the professors would go like 2-on-2 and like sit in the room and explain what you're doing and what your plan is for the rest of the term. And it was like, when I talked to them about how they designed the class, like when I was getting this job, I feel like that's the most important thing. Because you need to know when it's time to bail. Yeah. And like move on to something else if you need to. Especially if you're doing like, the ones that I've done have all been like semester long, like, you know, I don't even do the like methods week and the apply week. I just do it all, like do it with controls. The controls don't work, let's try again. And so they're really long-term projects. You just need to know when to fail.
Right, I just want to jump in, like, this reminds me of one thing I really, really want students to get out of an experience like this is that failure is a step on a path to learning, right? And so I've learned that if I control how they fail, as in, you know, it's in a structured way, okay, we had a meeting, it's heading towards failure, right? And let's just redefine the success, right? As opposed to I let them go all the way to the deadline and they fail catastrophically, right? It's a very different way to fail on the student's learning. Yeah. So yeah, I completely agree with Aaron. Like that's the most important thing is to check in on them and have a deadline, like an internal deadline.
Another thing I learned too is, right, the importance of setting it up at the beginning of the semester and being just very transparent about what your expectations are, about the idea that it's okay to fail, the idea that experiments might not always work okay, and that's part of the process. Just being super explicit about that. Like there was one year I forgot to do that when I was one of my first, and then everyone's like, oh, the lab is so disorganized, nothing worked, and then the next year, right, super explicit, like we're gonna fail and that's okay, it's part of the process and we're gonna celebrate just the process, right? And then the same failures happened and there was no disgruntlement at all, right? It's so much is about your attitude in pitching it and being transparent about it at the very beginning.
So much of it is trying to get them to see what research is like.
Yes,
this is what
this is
research is
real
like.
research, right?
Yeah.
You know,
It's
and
not
like,
that intro lab, right? The
Yeah.
cookbook one that you had, and yeah.
And so like you want to communicate that,
Yeah.
right? That's all it comes down to. And I think, you know, you want to communicate to them that like an experiment doesn't fail because you don't get the outcome you want. It
Right.
fails if you can't make a decision based on it.
Right.
And so if the decision is we're out, then you learned this is not a strategy to get to that outcome. And you say, okay, what would you do next time? And that's fine.
Yep.
Yeah, that's like how science works. Right? So yeah. That's pretty much it.
That's right.
Yeah, I have one issue based on this discussion. You had students who were really resistant to it. I think a lot of this conversation is focused on like the positives, and I think this whole group's pretty bought into the idea. But maybe not all students are, and some really. I think one of you just invoked the like many labs or the cookbook recipe, and it's not hard for me to imagine that some students find that very comforting and very safe, and then you're like, oh, go, be free, you know, go do your independent thing. And the student's like, okay, but what do I do first? You know, how much, what volume, and like, how do you manage that? Because in some way you want to support their learning and be like, oh, about 5 milliliters or something. But on the other hand, I feel like part of the goal is like, no, you do it. So I don't know if you have strategies on how you manage some students who kind of still want to like hold on to the rope.
I have a lot of students who are uncomfortable with uncertainty. And just having that conversation with them, like, it's okay, I'm here to guide you through this, and your lab partners are here to guide you through. Like, I think I see more uncomfortableness with uncertainty than I do resistance to this approach. But I think the scaffolding helps, right? Asking guided questions along the way, helping them arrive to that answer, to showing them that they can do it, that they can figure it out. So just, nudging and helping.
Yeah, I agree. I've been in circumstances where my course is not required. They don't have to take it. And so it selects often for students who want to have that experience, and that's, of course, nice. But when you're trying to do this with a course that is required, or they kind of have to take it, obviously more likely to be faced with that. I try to do a few things, and one is, make it. I think that transparency is probably the most important thing at the very beginning, is for them to understand what this is. This is an authentic research experience. You're going to be a scientist. You're going to behave like a scientist. You're going to think like a scientist. Science can be frustrating. It can be exhilarating. It can be all these things, right? And so they need to learn that. Often when I think a student is they don't like the uncertainty, and when a student is having a problem or just wants me to tell them what to do, I usually look at that as a situation where I think I need to understand the student a little bit better. Where are they coming from? what's this about? And, like I hope I said somewhere in the beginning, is I want all the students who come into the classroom to feel like they belong there. Some students will come in, obviously we know they come from different places, different experiences. Some are ready to go and others are not. And so I always give them the benefit of the doubt. If they're having that experience where they're saying to me that, I just want you to tell me what to do. What should I do? It could be that they're coming from, it's a lack of self-confidence, a lack in their experience, their background. And so I just take that opportunity to try and get to know them better, try to talk to them a little bit more. It's a lot more work, but I think it's to their benefit a little bit to help them understand why we're doing this. Some people we know are coming from an environment where they're just being told, right? The information flows from here to there. And this is the opposite of that. We're giving up control. We're giving them control, and they're very uncomfortable with that. And they feel like they're paying me to tell them and stuff like that.
Right.
And so they don't quite understand this. And so in some cases you have to literally give them the literature that talks about cures and what you're going to get out of it, So I find it tends to require a conversation. I'll sit down with them. I'll try to get to know them. I want to hear what they're thinking or what their fears are or concerns are.
All right, well, as much as I'd love to continue the conversation, we are unfortunately out of time, but thank you so much. I really appreciated all of your insightful and thoughtful responses to all the questions, and I really appreciated you all coming and for your participation as well.